So welcome back to this tutorial on polar coding. So today, yesterday we've seen the main polarization results, theorems. I will do a recap of that result, but mainly I'm going to be illustrating the algorithms today. So we'll be presenting this material in the context of channel coding. We will have a binary input discrete memoryless channel, input X, output Y, and the channel is denoted by W. X is going to be distributed on the alphabet 0, 1. The output alphabet can be arbitrary, even continuous, but for notational purposes, we will also assume that Y is discrete. So these are the transition probabilities. The probability of receiving Y, given that X is sent. I'll be making a symmetry assumption so that when I say channel capacity, it will be channel capacity. Linear codes in general do not achieve the capacity of any channel unless the optimal distribution is the uniform one on the channel input alphabet. So that's why I want to assume that the channel has some symmetries so that the capacity achieving distribution is the uniform distribution on the input alphabet. This way, I'm not going to have to say the symmetric capacity or the achievable rate with uniform inputs, etc. So when I say channel capacity, it will be the channel capacity due to the symmetry assumption. So essentially, there will be two easy channels, example channels that we will use, the binary symmetric channel and the binary erasure channel. These are symmetric channels. The capacity is achieved by the uniform distribution. Okay, and the channel capacity is going to be denoted by C of W. It's the mutual information with X uniform on the input alphabet because of the assumption that the channel is symmetric. So using log2 logarithms always, this number here will be between 0 and 1. Now the basic idea, this is another way of looking at it, in polarization is the following. Rather than trying to design a code, try to modify the channel so that coding is easy. There are two types of channels for which the channel coding problem is trivial. One is perfect channels. The capacity is exactly equal to 1, a noise-free binary input channel, you may say. Then you can just send the bits as they are. No need for coding. And then there are the useless channels. The channel capacity is equal to 0. So regardless of what you do, you cannot send any information anyway. We know how to do perfect coding, optimal coding for these two channels. And we don't know how to do it. Well, it is a difficult problem to do coding, except for these two trivial cases. The channel coding problem gets much harder immediately as soon as you are not in one of these two cases. So the idea, as I said, is to transform given channels, ordinary channels, W, into extreme channels, either this type or that type. Of course, we cannot do it perfectly. So you can never start with ordinary channels and achieve channels which are either perfect or pure noise channels. We cannot do it in an ideal fashion. But we will try to start with these, many copies of these ones, and obtain channels which are near perfect or near useless. So the method is essentially as follows. We take some number of copies of W, independent, and then we will combine them into a large channel by preserving the capacity in this combining operation. And then we will split this combined channel back into binary input channels of various different qualities. Some of these are going to be near perfect, some of them are going to be near useless. That's the idea. So before we design any code for these channels, we will do the channel transformation or channel polarization, and hopefully we will obtain extreme channels on this side, and the coding problem will vanish. That's the main idea. So how do we do the combining? The general architecture is as follows. We take n copies of the given channel. These are the channel inputs. And then we put a transform box here, a one-to-one mapping. So these are the channel inputs. These are the inputs to the combined channel, the vector channel. So this is a virtual channel that we've created now, that we will create by putting in here various different transforms. So this is now an n input, n output channel. And we would like to split this channel back into binary input channels. And the way we will do it is as follows. We will do it one by one. The first input, the input to the first bit channel will be U1. Okay, so let me follow the order in here. So what we would like to have here are uniform inputs, because we want to achieve the capacity of these channels. So I want to induce the uniform distribution on the axis. The way I will do it is I will pick a one-to-one transformation here, and I'm going to use IID uniform inputs on U1, U2, etc. Okay, so IID uniform here will give us IID uniform over here. Okay, so that way the total capacity of the vector channel here, which is the mutual information from the input to the output, namely this mutual information, is going to be equal to that one, because U and X are related to each other by this one-to-one transformation. And because the channels here are independent, this mutual information is simply the sum of the mutual informations across the individual channels. The channels are identical, so we have n times the capacity of the individual channels. Okay, so through this combining operation, in other words, we are not losing any channel capacity. Okay? It's a lossless type of combination operation. So we must ensure that we also will not lose anything as we split this big channel into pieces. And how do we split it? The chain rule is going to be our template or guideline. This mutual information, the total capacity of the vector channel, can be expressed as a sum of such mutual information terms. Now notice that there is UI here, a single random variable. It's a binary random variable. So the idea is to define a channel for which this mutual information term is the channel capacity. Okay, so each term here, we must ensure as we split the channel that these terms here correspond to the capacities of various binary input channels. So it's clear what we have to do because it is dictated by the form of these terms. The first channel, what is the first term in there? The first term under the summation is this one. So I have to define a binary input channel whose capacity is equal to this. The input will be U1. What will be the output? This is going to be the output. Okay, so these things are observed anyway, and I will pick this U1 as my input and this as the output. The output space is pretty large, but nevertheless, we have a binary input channel here. Okay, so now, okay, so that's going to be the first channel. Let me write in here the second channel. The second channel is going to have input U2, the second term in the chain rule expansion. And we have the entire output plus this additional term. Okay, so the notation is the superscript indicates this notation here is a subsequence starting at 1. So what we are looking at in this picture is the ith bit channel corresponding to whose capacity is equal to this term here. So the ith bit channel has input U sub I, and the output consists of all the things that are seen in here. So we see the Y, the entire vector Y, plus all the previous channel inputs, the inputs to the previous bit channels, in other words. Okay, so this, what we see here is a binary input channel, and the capacity of this channel is equal to that term. Okay, so this is the splitting operation. The ith bit channel, it will be denoted by W sub I, has input U sub I, and this entire collection of random variables as its output. So the capacity of this bit channel is equal to that. It's equal to this one. In the splitting operation, we have split the total capacity of the vector channel split the capacity into capacities of these individual bit channels, and we didn't lose anything. The total sum of the capacities is still equal to the sum capacity. Okay, so far so good. I think it is. This is just, playing with the chain rule. Okay, so what have we gained in here? Have we gained anything? Have we gained anything? First of all, why should coding this channel here be any easier than the original channel W? Okay, that's where we need the polarization result. So we certainly cannot hope to have this thing work with every GN. For example, say you take the identity mapping in here. Obviously, all the bit channels that you've created are exactly the same as the original bit channels. So what you need is polarization, which means you need to have here good mixing properties in addition to having a one-to-one mapping. Okay, so you can have very good mixing properties here by using, let's say, a randomly chosen one-to-one matrix, which has a lot of ones, etc. in it. And that's what we do in proving that linear codes achieve the channel capacity. We pick one linear code, the generator matrix, at random, with probability very close to 1, it will have full rank, and it will in fact achieve the random coding bound without the linearity constraint. So there is no question that there are many good matrices that you can put in here. But the question is, okay, suppose you put in here a good matrix. Then the problem will get extremely complicated. You have a huge output space, and doing ML decoding, even for a binary input channel, may be quite difficult. So the real essence of my talk here, polar coding, is to have a GN here, which has some structure, which achieves polarization, but can be implemented using low complexity encoding and decoding algorithms. Okay, so what I have said, let me say it again very quickly. Polarization is commonplace. Okay, so it's the rule rather than exception. You plug in here almost any matrix, you will have good polarization. A random permutation will do. And in fact, if you use a random permutation from binary n-tuples to binary n-tuples, this is equivalent to, permutation is not a matrix, of course. A random permutation is equivalent to Shannon's random coding approach. So I'm not saying that, polarization polarization is something new. Okay, we were using it, we've been using it. In the absence of it, you don't have any kind of coding theorem. So it's commonplace. If you use random transformations, you will have extremely good polarizers. They will be stepwise. So if you look at these channels that we've defined, they will, the first one will have capacity equal to 0, almost 0. So you will have a string of channels whose capacities are near 0. And then there will be a transition, a rapid transition from 0 capacity to capacity 1. And then they will saturate. So it is stepwise polarization you will observe. And then isotropic. What I mean by that is the following. Here I assumed an arbitrary order. I will first use this channel, U1, then U2, and so on. In polar coding, with structured matrices, the order here will be important. You cannot change the order and still hope to have polarized channels. With the recursive matrices, etc., that I will talk about, the order is extremely important. With randomly chosen matrices, the order in which you start and do the decoding is unimportant. So you can start in any order, you will still see this stepwise polarization. In that sense, it is isotropic. There is complete symmetry. These are obvious statements. Okay, I'm saying these things in order to point out what is different when we speak about, this other transform based on a recursive structure. So the random polarizers, they lack structure, hence they are too complex to implement. It is like choosing a random linear code. So what we need is, it would be desirable to have a low complexity polarizer. So in doing this, we can give up certain things. We don't need stepwise polarization. We don't need to have zeros followed by ones. It's okay to have some zeros, then a 1, and then going back down to 0. Okay, so having a irregular type sequence of zeros and ones, it's okay. And we can give up the isotropic property also if these are going to lead to a low complexity polarizer. Okay, so having said all of this, how do we do it? Okay, let's start with n equal to 2, just 2 copies of the W. This is the transformation G2 that we are going to be using. Okay, very simple transformation. So x1 here is the modulo 2 sum of u1 and u2, and x2 is simply equal to u2. u1, u2 are the inputs. This one should be looked at as the code word. This is the source word, if you like, and this is the code word. And this is the encoding matrix, encoding operation. So after splitting, this is the combining operation, the combined vector channel. After we split it, we obtain these 2 bit channels, W1 with input U1 and output Y1, Y2, just like we had over here with n equal to 2. And then W2, it has input U2, output Y1, Y2, and the previous input U1. Okay, so these are 2 bit channels that we've created. Let's look at them a little more closely. So for the first bit channel that we've created, U2 is part of channel noise. Okay, so it is like a random variable which is interfering with our transmission. That's how we treat it. And that's how it was chosen anyway. This is a Bernoulli 1/2 random variable, and it interferes with our transmission. In fact, if we didn't have Y2, the capacity here would be 0. But thanks to Y2, we have some, we can estimate U2 and subtract the estimate in some sense from the channel input. And then we have some useful capacity remaining for this channel. So the capacity is not 0 because we have this Y2, which lets us estimate U2. And the capacity of this channel is equal to that. The second bit channel, now as we look at or calculate the capacity of the second bit channel, we are doing something which will bother you. We are assuming that U1 is now known to us, known to the decoder. U1 is not known to the decoder because in general we are assuming that we use these to send data. Okay, so the decoder can only estimate this, and a significant number of times the estimate is going to be wrong. So how can we assume that the decoder for the second bit channel has perfect knowledge of the first input? Okay, so this assumption, so we need a genie. At this point, we assume that we have a helpful genie who provides this knowledge to us. As we go to higher order constructions, and as polarization takes hold, the channels are either going to be too noisy that we will not use them, we will not send any data over them. So what are we going to do? We will fix the input. When we fix the input, the decoder will also know how we fixed it. Okay, so there will be no need for a genie. If the channel is near perfect, then we will use it to send data. But for a near perfect channel, the previous decoders will each be able to estimate the input reliably. Once again, there will be no need to use a genie. Okay, initially we get help from the genie, but as the construction size grows, we don't really need genie as long as we do the right thing. In other words, don't send any data on unreliable bit channels. Okay, and as long as we have a good enough decoder that estimates, so that really means that we should be using only those channels which are sufficiently reliable. Okay, so there will be error propagation. In other words, you have this sequence of channels. If you make an error in the ith bit, all the remaining, that error propagates. So the goal is not to make any errors all the way through this decoding sequence. So the decoding, as you see, it's going to be based on successive cancellation. It will be done one bit at a time, and it will succeed only if all the bits are decoded correctly. Okay, so now this case, n equal to 2, contains in it all the main ideas. First of all, there is conservation. This is a rewrite of what we've seen before. The sum of the capacities of these two channels, which is 2 times CW, equals the sum of the capacities of the bit channels, the synthetic channels that we've created. There is conservation of channel capacity. And then we see the first trace of extremization. The capacity of W1, the first bit channel, it is less than or equal to, it is upper bounded by the capacity of these channels, the row channels. And then the capacity of the second bit channel is at least as large as CW. Why is this the case? Look over here, the second bit channel. The second bit channel, this one. Okay, let's write it again. I of U2. The channel output is Y1, Y2, and U1. So U2 is equal to X2. U2 is equal to X2 here. Okay, so if I throw away these terms and look at only the mutual information from X2 to Y2, this is equal to C of W. Okay, so these other things, Y1 and U1, can only help you. So it is pretty clear that this term here is greater than or equal to that. And this inequality follows from the conservation then. It's not difficult to see that this is true directly either, but it's trivial to see that this inequality holds. So important thing in here is to understand the condition for equality here. So when can we have CW2, namely this, equal to that, I of X2, Y2? Well, it turns out, and it's easy to see, that we will have equality here if and only if W is an extreme channel. In other words, if and only if W has capacity equal to 0 or 1. In all other cases, you can also see what's happening. I mean, if I'm given U1, let's look at it this way too. Suppose I'm told what U1 is. The genie is telling me what U1 is. Say U1 is 0. Then I'm sending this U2 twice. There is diversity 2 transmission here. I'm sending it twice over 2 independent copies of the same channel. So it's clear that the capacity of that diversity channel is going to be larger than CW unless the channel is either pure noise or perfect. So this should be clear enough. So typically what we have for ordinary channels, we will have strict inequalities here. So we begin with channels of uniform capacity CW. At the first step, what we do is we create two channels, one worse than the original channel, the other better than the original channel. So these two channels, we may view this operation as beginning with two channels and manufacturing two new channels, W1 and W2. For more suggestive notation, let's use W minus and W plus. Minus indicating that it is a worse channel, plus indicating that it's a better channel. Now, the next step is going to be the following. We will take two copies of W minus and then apply the same trick on W minuses. We will do the same thing as we generate two copies of W minus. We will also be generating two copies of W plus. So we will also do the same thing on W pluses. Okay, in the next step, size 4 construction, we will have 4 channels. W minus minus, W minus plus, created through this operation with W minus and W minus here, and W minus minus, W minus plus in here. And similarly for the other two channels. So here is the size 4 construction. We have, this is the size 2 construction. We repeat it, okay? Now at these terminals we have W minus and W minus. W minus here and W minus here. What is the next step? I want to combine W minus and W minus in the same way I have combined these two. So here are the W minus channels. Okay, so these are virtual channels now, but they are, yes. So what we do is we combine the inputs of W minus and W minus and combine the inputs of W plus and W plus. So let me go back to this picture. Here we had W minus and W minus, a U1 here and U1 prime, if you like, in here. I combine U1 and U1 prime. Okay? So that's what we obtain. Now the decoding order is important, it's crucial. How are you going to do the decoding? In which order are you going to disentangle this combination of channels? Okay, so let's spend some time on this. Okay, so we had two W minuses. Okay, so let's put this. So I have a U1 here, and I have another U1 here. Okay, U1 and U1 prime. I have a U2 here, I have a U2 prime in here. Okay, so now I won't do the combination of U1s and U2s all at the same time. Okay, let's first do the following. Okay, so I left the U2 channels as they are. I combined the U1 channels. Remember, the U2 channel is becoming accessible only after U1 is decoded. Okay, so let's look at some decoding orders. The one that I'm suggesting is this one. We will first decode this one. I must decode the U1 channels before I decode the U2 channels. I will first decode this one. Why? the U1 was here. Okay, so let's use the okay, so this is U1 and this is U1 prime. Let's use something else for this. They are no longer the same inputs. Okay, so U1 and U1 prime, they have been combined. Let's call this V1. The first channel that I'm going to decode, this is going to be the second channel that I will decode. Okay, so when I do it in this order, I will have removed U1. I will have knowledge of both U1 and U1 prime. If I know V1 and V2, I know U1 and U1 prime. Knowing U1 enables me to do decoding on U2. And knowing U1 prime enables me to do decoding on this one. If I try the different decoding order, say, first this one and then this one, would it work? It would indeed work in this example. Okay, so because all I need to know to decode U2 is knowledge of U1. I have it, so I can do the decoding. I can decode U2 after V1. Okay, so that's fine. Let's ask the following question. Can I decode this one after that? Can I decode this one after decoding that one?
Can you repeat the last step?
Okay.
Because U1, I would need U1, right? But if I have V1, I don't know U1.
So there are this channel here. Let's write them over here. I have a channel. The second channel I have has input U2. Okay, and then it will have outputs. This is output Y1, Y2. Let's call it Y1 prime, Y2 prime. Normally, I don't call them prime, etc. This is Y1, Y2, Y3, and Y4. But, okay, so we started with two independent copies of size 2 construction, and we are now coupling the two constructions, okay? So initially, this is what we had, right? Yeah. Okay, so what I have, let me start over again. I have a U1 channel and U1 prime channel. These things are virtual channels, but they are channels. Okay, abstractly, they are channels. So there is nothing that should prevent me doing on these channels, namely these channels, U1 going to Y1, Y2, and U1 prime going to Y1 prime, Y2 prime. I have 2 bit channels. So I want to play the same game on these channels. How do I do it? I take the input of this one and then combine it like this, okay? I'm not doing anything else. Okay, can I disentangle these things in the same way I have been doing it?
No, my question was why I cannot. You said actually I could decode U2 after V1.
Yeah. Okay, so what is the channel U2? It is the channel Y1, Y2, and U1. This channel here requires knowledge of Y1, Y2, and U1. So as soon as you have U1, I'm sorry, yeah, you're right. So you are saying I don't have U1. I have V1. Okay. I apologize for it. Yeah, you're right. Okay, so I have to decode this one. Okay, thank you for pointing that out. I have to decode this one so that now the sum of V1 and V2 gives me U1. And having U1, I can go ahead and decode this channel, this one. Okay, then, look, do I have to decode this one next, or can I decode that one? That one is the third channel. Decode this one as V3, or decode this one as V3. Both choices are possible here, okay, because you have the required knowledge for decoding either this one first in the third order or this one in the third order. Okay, so on the other hand, that's the next step in the argument. Why not do the same thing simultaneously on these two bit channels as well? Okay, so we had these two channels, virtual channels that were created, and we combined and split them. Why not do the same thing on these ones as well? Like that. Does this combining operation here perturb the decoding on V1 and V2? This is the important question now. Does this system in which I apply, let's call it V3 now, and then V4. Okay, so if I do this, apply the data inputs as V3 and V4 rather than as U2 and U2 prime. If I apply them like this, does this change anything? Well, what is the distribution of U2 and U2 prime? What was it? It was the uniform distribution. So what is the distribution of V3 and V4? The uniform distribution. So the uniform distribution induces uniform distribution over here. So nothing changes. More important perhaps is the following. This transformation here is 1-to-1, okay? So it's a 1-to-1 transformation by, I don't change the statistics of U2 and U2 prime. In decoding V1 and V2, I'm not assuming knowledge of U2 and U2 prime. All I am assuming is that they are uniformly distributed. Okay, so by doing this combining operation and applying uniform inputs at V3 and V4, I don't perturb the uniform distribution on U2 and U2 prime. Hence, it's okay to simultaneously couple both inputs. Okay, this is a little tricky, but and it is not very clear when you do it by slides. Okay? So this is the only possible decoding order, the correct decoding order. If you do not couple these two, then, okay, that should be the first. This is the second. Either this or that may be the third one. But after coupling, this has to be the third input to be decoded. Okay, if you have followed me so far, you've understood it all. I mean, the rest is simply, repetition of this structure. So if you did not follow anything, please ask. Okay, I will do my best to explain it. This is really the crucial point in understanding the construction. So to summarize, you see, we have a size 2 construction, 2 independent size 2 constructions, 2 virtual channels, synthetic channels that we've created.
So maybe question is, so if you do so there are 2 different orders you can do, right? One with this bit reversal and one without. So,
pardon me?
So there are 2 different orderings which end up working, right? One where you do this bit reversal permutation and one without. So
now, there is no bit reversal here. The bit reversal is applied over here. Okay, I'm hiding the bit reversal issue in this presentation. Okay, so there is no need to, okay, maybe the bit reversal is here. Let me answer the question this way. You see, the order in which we are decoding these is the bit reversed order. So the first input, okay, so the Let's represent integers with bits. Let's also clarify this point. In using bit reversal language, one should really index these things starting with 0. Okay, so natural numbers are no good. Okay, so the order should be 0, 1, 2, 3, and then you turn these things into binary representations. So the order in which I'm doing the decoding is this one, in bit reversed order. I'm first decoding, this one, index 0. Fine. The next thing I'm decoding is this one, the third wire. It has index 2. Okay, so I'm decoding this one, the third wire. It has index 2. Okay, so it doesn't have index 1, but it is, if you bit reverse everything here, you get the order in which I'm doing the decoding. So this is the normal order. And then this is the bit reversed order. The decoding, if you look at the wires, in which order I'm doing the decoding, I'm first decoding the wire with label 0, 0. That's the first one. Then I'm decoding the wire with index 2 that has this label 1, 0. But if you do bit reversal, okay, you can read the exact ordering in which we do the decoding. Now, the bit reversal is something which can be avoided in this exposition. I would like to avoid it because it is just, for convenience in writing down the mathematical formulas. You want to write the chain rule in such a way that the indexing is in the natural order, not in the bit reversed order. So at some point you say, I'm going to put in here a bit reversal permutation so that the chain rule can be written in the natural order. So it has really nothing to do with, the order here should be understood by looking at the picture. Okay, so, and there is only one logical order in doing the decoding in here. So let's go to, yes?
Why not U1, U3, U2, U4?
Let's go back. Say it again, please. U2.
So the order you mentioned was U1, U2, U3, U4, right? You first decode U1.
The order of decoding is U1, U2, U3, U4, yes.
Why not U1, U3, U2, U4?
It doesn't work. Why doesn't it work? Now, okay, so if I first decode U1, and then which one, U3? Now, you are not then, okay, you decode the first channel, that was a W minus channel, okay, so you had 2 copies of W minus and 2 copies of W plus. Okay, you combine these ones, and what you want is to obtain W minus minus and W minus plus. Okay, only after you decode the second one that you will have this one appear as W plus. Okay, so unless you decode this U2, so you are saying U1 and then this one, right? Yeah. Okay, so now, what is this channel that you are seeing in the presence of only U1 and not U2? Okay, so the channel you have there is U2 to U3 to, sorry, you want to decode U3 before U2. So these are all available to you. Let's write all of them. Y1, Y2, Y3, Y4. Okay, and what else? You have U1 available. You don't have U2 available to you. Now, What you want is something like this. U3, Y1, Y2. Okay, now for okay, we've decoded this one, now we are decoding that. Okay, U3. Let me see. Now the interference that's coming into this channel
It's only from U4.
is coming from U4, but you see U4, it doesn't show up very clearly in here, is not a W plus channel yet. It will become a W plus channel only after you decode U2.
Oh.
This is W minus W plus, but these are virtual channels. This will become W plus, and that will become W minus only after, if we go back to, the picture, if I have a picture, yeah, this picture is better, yeah. Okay, now you are suggesting do U1 first, and then do U3. Okay, so look at U4. U4 is, at this point, U4 is only a W channel. Okay, it's not a W plus channel. So you have a different, the formulas get mixed up. I'm not saying that it is not going to work.
No, but my question more
The
fundamentally.
recursive structure will get,
Unique, or is it not unique? Is the order in
the order is, well, I mean, obviously you can choose any decoding order you want.
Right,
The question really is, will it polarize under any decoding order? I can show you very clearly that it will not polarize. For example, if we start with U4.
No, I can understand. So here is what intuitively I'm thinking.
Yes.
Now, when you polarize a channel, there is a good channel and a bad channel.
Mm-hmm.
So U1 was polarized through two bad channels.
Yes.
U4 went through two good channels.
Yes.
So it seems to me that you want to first decode U1, or equivalently, you want to fix U1. It's going to be a really bad channel, right?
Yeah, this is going to be a bad channel, yes.
U4 is going to be a good channel, assuming...
If all the previous ones have been decoded, this is going to have diversity 4.
Clear to me is between U3 and U2, because it went through one good channel and one bad channel.
Okay, now don't think only in those terms. Also think in terms of the recursion. Okay, preserving the regularity of the construction. Okay, or maintaining analytical tractability. Okay, so that's why I showed first. I'm not saying that it is not going to polarize under various other decoding orders. This is not a claim I'm making, but I'm not going to be able to analyze it. Okay, because you see here I'm ensuring that in this decoding order you combine two W minuses and then two W pluses. If you do it in some other order, what you will be doing is you'll be combining various different channels. The channels that are combined and split are not going to be identical. What happens then is, who knows? It may still polarize, it may still work, but this is, if you like, this is the suggested order. So now we have the size 8 construction. We create two independent copies of the size 4 construction. And I changed the wiring order a little bit. Now you see that I'm doing the decoding in the natural order. Okay, so a bit reversal permutation has been applied in this transformation. The wiring has changed a little bit, if you have noticed. Okay, we had the adjacent nodes connected to each other near the channel. Now they are connected to each other at the source. Okay, so this is the difference between bit reversed order, and the natural order. Okay, so but look at this cross section here. There are 4 wires here connecting the bottom half to the upper part. Okay, so if you cut these wires, you have 2 independent copies. Okay, so the way you want to proceed with the decoding is, you know, you connected this one and that one, you will unentangle it first, okay? So first this one, then that one. Move to the next one. Okay, if you do it in the order that, did I say it correctly? Maybe not. Okay, well, anyway, this is the construction. The decoding order is, okay, I wish I had drawn it the other way around. Okay, so the decoding order, yes, we can do the decoding in this order. First this one, then this one, okay, then that, and this one, bit reversed order. Huh?
I think you just proved the point that there are different decoding orders.
The decoding order.
In which you get polarization. This is just a different decoding order.
Yes.
You go from top to bottom, you still get polarization just because you drew the circuit differently.
It doesn't make any difference. Yeah, because you have the same signals appearing in here as the ones over here. Okay. So, well, I'm running out of time, so I will stop in 2 minutes. Whether I won't be able to get through all the intended material, but let me just illustrate what happens if you keep doing this transformation. So we have a binary erasure channel. The binary erasure channel has the nice property that when you do the combining and splitting operations, you create only binary erasure channels. And then it's easy to calculate the capacities of the W minus W plus channels. So if you combine two W's, this is the W minus you obtain, the erasure probability gets transformed as 2 times the erasure probability of the original channel minus epsilon squared. And the erasure probability of the better channel is epsilon squared. So this is the better channel. And these are the capacities of the binary erasure channels that we create by this construction for size 16. So the original channels are binary erasure channels with erasure probability a half. And it's a size 16 construction. The first channel has capacity almost 0. And then the second channel, the third channel. Now this is the reason why I drew the figure in that different order is now we are doing the decoding in natural order. And you see that at small indices, we have some very bad channels. And as the index gets large towards the end, as you might guess, the capacity approaches becomes near 1. So 16 is too small a size for such constructions. We don't yet have polarization. But as you keep increasing the size of the construction, most channels are either at the very bottom or at the very top. So you go to higher lengths, although it is not clear from the figure, the fraction of channels for which the capacity is between 0 and 1, namely those mediocre channels, that fraction is going to 0. It is difficult to see it from the figure. So this, I think this is a good point for me to stop. And next time, I'm going to talk about the martingale for analyzing and proving the polarization. There is a martingale here. This is another way of drawing the same figure. This is size 2 to the 7 construction, 128 nodes in here, and they correspond to the capacities of various channels created. And then there is this traceability. Okay, so you create 2 channels, a good channel and a bad channel. This has 2 descendants. Okay, so if you do the combining and splitting in the order that I have described, what you have is a martingale. The expected value of the capacities of the children is equal to the capacity of the originator. Okay, so you have a martingale in here, and then it's a bounded martingale between 0 and 1, and you have all the nice properties that comes with bounded martingales. It converges in almost surely in L1, L2, you name it. Okay, so you not only have the capacities here converging, but they also are stable. Okay, so you, for example, this converging to 0 does not oscillate, or the fraction that does oscillation also goes to 0. Okay, so you need this. This is important because otherwise, as you change the construction size, good channels could become worse channels and so on. So the whole thing could reshuffle itself, and you wouldn't be able to use it. So it is not just for the sake of proof, but also for gaining practical insight. It's important to understand the martingale nature of the construction here. So with that, I will stop and see you tomorrow. Thank you very much.